A forward contract is an agreement to buy or sell an asset at a specific time in the future for a specific price. Forwards are sold in the over-the-counter market and negotiated directly between a buyer and a seller. The buyer assumes a long position and the seller assumes a short position. And the forward price is the pre-specified price in the future. We denote T, the time to deliver the forward contract, K, the forward price, ST, the market price of the underlying asset at time T. If the market price of the underlying asset at time T greater than the forward price, the holder makes positive profit by locking their lower price for the underlying through the contract. If the market price is less than the forward price, the holder realizes a loss by locking the higher price for the underlying through the contract. And the payoff is ST minus K. For selling forwards, using similar reasoning, the payoff is K minus ST. Futures are similar to forwards, but traded on exchanges. Now talk about options. A call option is option to buy a certain asset by a certain date at a strike price, and a put option is option to sell a certain asset by a certain date at a strike price. An American option can be exercised at any time during its life. An European option can be exercised only at maturity. We use C for the price of the call and P for the price of the put. An European call option gives the option holder the right to buy the underlying asset for price of K at maturity. If the underlying asset price is less than K, and the holder does not exercise because it is cheaper to buy the underlying asset in the market, the holder's payoff is 0 and the profit is negative C. If the asset price at time T greater than the strike price K, then the holder exercises, and the payoff is ST minus K and the profit is ST minus K minus C. And in general, the formula for the payoff is max of ST minus K and 0, and for the profit is max of ST minus K and 0 minus C. An European call option obligates the option writer to sell the underlying asset for price of K at the expiration date if the option holder desires to buy it. If the asset price at time T less than K, the holder does not exercise because it's cheaper to buy the underlying asset in the market, and the writer's payoff is 0. The profit is equal to C. If the underlying asset price is greater than the strike price K, the holder exercises, and the writer's payoff is negative of ST minus K, and profit is C minus ST minus K. The formula for the payoff is negative max of ST minus K and 0, and for the profit is C minus max of ST minus K and 0. An European put option gives the option holder the right to sell the underlying asset for a price of K at the expiration date. If the asset price is greater than the strike price K, the holder does not exercise because it's more profitable to sell the underlying asset in the market, and the holder's payoff is 0, and the profit is negative P. If the asset price is less than K at maturity, the holder exercises, and the holder's payoff is K minus ST, and the profit is K minus ST minus P. And the formulas for the payoff is max of K minus ST and 0, and for profit is max of K minus ST and 0 minus P. An European put option obligates the option writer to buy the underlying asset for price of K at the expiration date if the option holder decides to sell it. If the asset price at maturity is greater than the strike price K, the holder does not exercise because it's more profitable to sell the underlying in the market, and the writer's payoff is 0, and the profit is P. If the underlying asset price at time T is less than the strike price K, the holder exercises, and the writer's payoff is negative K minus ST, and profit is P minus K minus ST. And the formulas for the payoff and profit correspondingly, the payoff is negative max of K minus ST and 0, and profit is P minus max of K minus ST and 0. Now take an example of a call option. The strike price K is $52, and the maturity T is 0.5 years. The current price of the underlying asset is $50, and the risk-free rate is 10%. And suppose at time T of 0.5 year, the stock price may go up to $60 with probability of 0.6, or go down to 42 with a probability of 0.4. If the stock price goes up to 60, then the value of shares, the total shares, is 60 delta, and the value of the call option is max of 60 minus 52 and 0. That is equal to $8, and the total value of the portfolio is 60 delta minus 8. And similarly, if the stock price goes down to 42, then the total value of the portfolio is 42 delta. To be riskless, the future value should be the same. So that gives delta of 0.44 something shares, and correspondingly the total value of the portfolio can be obtained, which is $18.67. And since the portfolio is riskless, it must earn the risk-free rate of interest. So discounting one period of 0.5 year, then you get the portfolio value today, and from there you get the price of the call, which is $4.46. Assume that the stock price today is S0, and in given period delta T, it can go up to U S0 or down to D S0. Then what is the value F of an option written on the stock? So here we let FU and FD the payoffs of the derivative. We take long position in delta shares of stock and short position in one call option. Then the portfolio value in the up state and down state can be obtained. And to be riskless, they have to be equal. From there, we obtain delta. the portfolio present value and the portfolio value today can be obtained. Let them equal. We get the fair value of the option today. Go back to the previous example. We can get U, D, FU, FD, and probability P and Q, which is 1 minus P. And from there we can get the value of the core options following the formula in the previous slide. This slide shows the generalized formula for multiple pairs. Now we talked about the Black-Scholes model for European core input. Consider a vanilla option like European style core option written on a non-dividend paying stock, whose price ST follows a geometric Brownian motion. We can show that the value of the option F at time t depends on the time to maturity and the current price of the underlying asset, and satisfies the stochastic differential equation. At maturity, the option value is mix of the asset price at maturity minus K and 0. To get rid of the randomness, we use options and stock shares to view a portfolio whose value is deterministic. Consider a portfolio consisting of a short position in an option and a long position in delta stock shares, and the value of the portfolio can be obtained. And from Ito's lemma, we can get to this step by neglecting terms with order higher than dt and ds, differentiating the value of the portfolio, and select delta so that the portfolio is riskless. And because it's riskless, it earns the risk-free interest rate. Let the pi here and there equal. We get this. And finally, we get to this deterministic partial differential equation. It's difficult to get a solution in a closed form, and it's normally solved using numerical approaches. And there are a few cases the equation can be solved analytically, and that is the case due to Black-Scholes. And we have the solution for a European call and put, in which S0 is the current stock price, capital T is time till expiration, K is option strike price, R risk-free rate, Q the dividend yield, phi cumulative standard normal distribution, and D1 and D2. Sigma is standard deviation of stock returns. We can derive the equivalency relationship between the binomial tree and Black-Scholes model. This space shows the multi-step binomial tree. At a step, the stock price in the following step may go up by an up factor or down by a down factor. As the last step or the last period, the value of the European call or American call can be calculated as a mix of the asset price at maturity minus a strike price K and 0, and the value of the European put or American put can be calculated as the max of the strike price minus the asset price at maturity and 0. In other periods which are not the last period, the value of the European call or put is the expected value in the following period, discounting back by one period. The formula for the American call and put are a bit more complex because they can be exercised anytime. So here you can see the max function. So repeat this process backward in time back to time 0. We can calculate the value of the option. Let's look at option pricing using trinomial tree. With trinomial tree, given the usual equation, we write the moment matching equations. And solving the system, we get the probabilities PU, PM, and PD, which are the probabilities of going up, staying the same, or going down. For going up, the asset price may go up to from x to x plus delta x, or may stay the same or go down to x minus delta. The value of an option written on an asset at the price ST at time t satisfies the partial differential equation. In order to solve a PDE by finite difference methods, we need to set up a discrete grid. Let T be the option maturity and S max is the largest asset price. We create a grid containing points ST like this. This page shows the approximation of partial derivatives in the previous equation. And basically, we have the derivative of f with respect to the asset price S, as well as with respect to the time t, using the forward difference, backward difference, central or symmetric difference, as well as the second derivative. At expiration, the terminal condition is the option price is the max of the asset price minus the strike price and 0 for a call option, and the max of the strike price minus the asset price and 0 for a put option. Considering the boundary conditions with respect to asset price, the problem is not so trivial because we have to solve the equation numerically on a bounded region, whereas the domain is unbounded with respect to asset price. Consider a vanilla European put option as example 1. When the asset price S of t is very large, the option is worthless, or we say it stays out of the money. When the asset price is 0 and it remains 0, the payoff at expiration is K, and discounted back to T. We have the option price at time T. And this is the grid notation. In example number 2, we consider a vanilla European call. When the asset price is 0, at any time t, the option will expire worthless. When the asset price is very large, we can be sure it is in the money at expiration. The payoff S minus K, discounting back K to time t. The arbitrage-free price at time t for the underlying asset is X. And from there we get the boundary condition. And this is the grid notation. Now let's see how we can price a vanilla European option by an explicit method. We approximate the derivative with respect to the asset price by a central difference, and the derivative with respect to time by backward difference. And we use the boundary conditions for the put options previously discussed. Solving this, we go back in time. Let the index j equal to n. Given the terminal condition, we have one unknown quantity fi at time n minus 1, expressed as a function of 3 known quantities. And we can repeat this again and again, similarly for other quantities, other unknown quantities. Let's see how we price a vanilla European option by an implicit method. Here we use a forward difference to approximate the partial derivative with respect to time. Here we have 3 unknown values linked to 1 known value. Note that for each time layer we have n-1 equations in n-1 unknowns. The boundary conditions yield the 2 missing values for each time layer, and the terminal conditions give the values in the last time layer. Similarly as in the explicit case, we go back in time, solving a sequence of systems of linear equations. This slide shows the system for time layer j. Monte Carlo simulation is widely used in computational finance. It may be used for evaluating portfolio management rules, for pricing options, for simulating hedging strategies, and for estimating value at risk. The starting point for the application of Monte Carlo simulation in option pricing is the generation of sample paths of the underlying factors. Consider an stochastic differential equation for asset price. We can simulate the asset price St over the time interval from 0 to capital T, discretized using a time grid where the time increments are equally spaced with the width dt. Integrating dst from t to t plus dt, we have this with 3 terms, and this is the starting point for any discretization scheme. At time t, the value of st is known, and we need to get the next value at t plus dt. Euler scheme is the simplest way to discretize the process. is equivalent to approximating the integrals using the left point rule. We get the first integral, the second integral, and then finally. So here we see that the distribution is normal rather than log normal. Using very small dt reduces the error, but it's time consuming. Now we use Ito lemma for simulation of Brownian motion. Let's consider the geometric Brownian motion model. Using the Ito lemma, we get to the step, and this is the some lines for Ito lemma. And we may notice that the derivative of log of st with respect to st is 1 divided by st, and that cancels out the other st, and so finally you have just sigma in the second term. Similarly, the derivative of log of st with respect to st is 1 divided by st, that cancels the other st, and that's why we have just mu left as the first term in the brackets. And the second derivative of log of st with respect to st give negative of 1 divided by st squared, and that cancel out the other st squared, and finally you have just 1/2 of sigma squared. And the derivative of log of st with respect to t is 0. And from there, taking the integration of both sides, we have this. We need to discretize time with time step delta t to simulate the path of the asset price over an interval from 0 to capital T. Recalling the probabilities of a standard winner process, we get this. And epsilon is the standard normal random variable. Now we can generate sample path for the asset price. This slide shows the reminder for Ito lemma. Given an Ito stochastic differential equation, which can be considered as a continuous limit of another. And notice the differential of a function g of x and y, which may be from the Taylor expansion. Neglecting the higher order terms and taking the limit as both delta x and delta t tends to 0. And the differential of a function f of x t of xt can be given. And then replace the x in, we get Ito lemma. This slide shows how to use multi-color simulation to price a European style exchange option written on 2 assets whose price model as b-dimensional geometric Brownian motion. The correlation between the 2 winner processes is rho. The option payoff at maturity capital T is max of the asset price V at maturity minus the asset price U at maturity and 0. This allows to exchange one asset for the other at maturity. For example, if we hold asset U and one exchange option, then the payoff at maturity is given here, and the analytical solution can be obtained, which is the generalization of the Black-Scholes formula. We can also use multicolor simulation, and we need to generate two independent standard normal variables to simulate bidimensional correlated linear processes. And they are epsilon 1 and epsilon 2. Z1 and Z2 are normal distribution, standard normal distributed. This slide shows how to price an arithmetic average Asian option using multicolor simulation. The option payoff is given, in which the option maturity is capital T, and time ti is I times delta t, and delta t is t divided by n.